Yeah? So folks, if you remember, we were talking about heteroscedasticity in the last class. Actually, the taxi, they don't make it. Of course, can't escape either. काम तो दोनों में करना पड़ेगा. Both define very essential skills for economics. So we are talking about heteroscedasticity. What do you mean by heteroscedasticity? What do you mean by heteroscedasticity is a question which I am throwing at you. The variance of error term is not constant. Correct? Everybody agrees with this? The variance of error term is not constant. So what do we do? If the variance of error term is not constant, what are the implications? Is the OLS estimator still unbiased and consistent? Yes. Why? Because the consistency of the OLS estimator depends upon the covariance of x and e being 0. As long as the covariance x and e is 0, whatever happens to the distribution of the error term, the OLS estimators will continue to be unbiased and consistent. Right? So why should we worry about heteroscedasticity? Yes, the variance of the beta hat estimator is no longer sigma square upon summation xi minus x bar square. Is no longer sigma square upon xi minus x bar square. It's a different formula. So what happens if you use the wrong estimator for the variance of beta hat? Our t values go wrong. Yeah? And what happens if t values go wrong? Tests of hypothesis go wrong. Yeah? And therefore it is absolutely important that we get the correct variance coefficients. Correct estimates of the variance of beta hat. Because ultimately beta hat by itself, the estimate is of little value to us. Because we are not interested in beta hat. We are interested in beta. Beta hat we are interested in, we calculate beta hat as an estimate of it. On the basis of this beta hat, we are going to make some guesses about what the actual beta is. And we use tests of hypothesis to test the validity of those guesses that we make. Right. So it's absolutely important that our hypothesis testing is correct. Yeah, sometimes even more important than estimating beta hat, it's more important to actually say something about the true value of beta hat on the basis of the beta hat that we got. And therefore, what is really important is the hypothesis testing part. So the hypothesis testing part is not right, you're going to face problems in estimating in your analysis. Sure? So we need to get that right. So how do we get that right? We have done something in class. We did a GNS, we did a weighted least squares, and then we did how to find that weighted least squares, how to empirically implement it, and which we called it feasible generalized least squares. Right? Okay. Now, so we know what are the implications of heteroscedasticity. We know how to correct heteroscedasticity if there is any. We still don't know how to find whether your data has actually heteroscedasticity in this domain. Whether there is heteroscedasticity at all. We need methods of finding out whether there is heteroscedasticity at all. Only after we decide and we determine if there is a problem with heteroscedasticity shall we be able to, if there is a point in defining methods for correcting heteroscedasticity. Right? Okay. So let us now in this class we will study various tests of heteroscedasticity. We will study 3 tests of heteroscedasticity. One is the classical Goldfeld-Quandt test. Okay, the classical Goldfeld-Quandt. I'll write that on the board, so don't worry about that. But it's not really a very useful test for a large number of reasons. Nobody really uses the Goldfeld-Quandt test. So we'll look at two more general tests. Box means one is called the BPG test, right? And the other is called White's test. So we're going to look at this, yeah? So these three, Box-Pierce-Godfrey test or the, White's test. So there are two tests that we are going to learn to test for heteroscedasticity. Then we are also going to explore an alternative approach for heteroscedasticity. With emptiness, what did we do? We transformed our data in such a way that the resultant model did not have heteroscedastic distributions. An alternative approach is to simply say, if sigma square upon summation xi minus x bar square is not the correct formula, what is the correct formula and how does one implement that correct formula? Right? Okay? So we are going to also look at that correct formula, which is called White's heteroscedasticity consistent variance covariance, standard errors. And then we are going to go to a very realistic situation. See, so far we have been studying about one problem at a time. So we said, suppose my x variable is endogenous, then I have an instrumental variable. If my error terms are heteroscedastic, then I use FGLS or something else, right? But the real world is not kind to you. It doesn't throw one problem at a time at you. It throws several problems at the same time. So what will you, for example, do if your x variable is measured with error and the residuals are heteroscedastic? Right, so we also learn to think of those kinds of problems in today's class. Fine. So first let me take you to the Goldfeld-Quandt test. It's a classical test coming from the 50s. Yeah, please remember that during those days we did not have fast computers and most regression equations were quite simple. Right? So very often you had a single explanatory unit. Yeah? And then we had all sorts of other things like the error term being normally distributed and so on and so on. Right? So they didn't exist very strong enough computational technology. Computers came only in the 80s. Calculators came a little bit before that, in the 70s or the 50s or the 40s, and then really. So people had to actually sit down with pen and paper and calculate things and so on. So therefore most computational problems were very simple. Right? So what do you do in the Goldfeld-Quandt test is, suppose you have data, okay, say y, suppose y, suppose you have x2, x4, x5 and so on. So what you have is, you have the pairs. Here are the pairs. I going from 1 to 10. The first step that you do in the Goldfeld-Quandt test is to arrange these pairs in the ascending order for x. The first step that you do is to arrange these pairs in the ascending order for x. What do I mean by that? So suppose I have y and x. So 3, 4, 5, 2, 6, 9, 7, 3, 8, 1. So here these. Right, so it says, put this, rearrange your data like this. Rearrange your data like this. Y, x, 1, 8, because that's the lowest value of x. What should come next? 2, 5. You have to arrange x in an ascending order. What will come next? Yeah? Then what will come next? Yeah? 4, 3. And 9, 6 is what will come. Right? So you arrange the data in the ascending order for x. Right? Now suppose you have n observations. You realize 5. Suppose you have n observations. What you do is, you take out a middle k observations away. So delete the middle k observations. Say for example 60 observations and k is 20. So you leave the first 20, leave the last 20, remove the middle k. Pardon? No, it has to be ascending order for x. 1. So you have to take this is 1. You have to take the lowest x. Right? In fact, you have realized one of the problems is this. I have one mistake between 2 there and I would have had a tie in the room. So I have kept down the room you want. Right? At least you see one of the potential problems with this is sure? Right folks? Okay. So you have 1, 2, 3, 4, 5. Right. So suppose you have n observations. You remove the middle two. Right? How many observations are there? N minus 2. Right? How many observations will be the first part? N minus k by 2 will be the first part. N minus k by 2 will be the last. If you remove the middle k observation. Right? In such a way that roughly equal number of observations are in the first. So basically divide your data into 3 parts. Remove the middle third, keep the first third, keep the last. Right? Suppose we do this. So in the first part of the data, I have n minus k by 2 observations. In the second part of the data as well, I have n minus k by 2 observations. Yeah? Have you done the F test in class? Yes or no? Yeah? F test is a restriction of regression coefficients. Please, when do you use the F test? When you want to compare two sample variances. When you want to compare two sample variances. So what you essentially do is, you run a regression on the first 1/3 of the data, you run the same regression on the last 1/3 of the data. Right? So in the first 1/3 of the data, you run the following regression. The first 1/3 of the data, you run. Where E1i is the error term in the first 1/3 of it. Okay? And then, so I'll call it Y1i, alpha 1i, beta 1i, S1i. Right? You also run as a this regression on the last 1/3 of the data. Now, so you will get E1 hat I from the first regression. Yeah. E hat 2i from the second regression. Okay. Now, assume, so summation E1 hat I square upon n minus k minus 2. N minus k, actually this should be n minus k by 2 minus 2. This one. Because I have removed the k observations in the middle. So n minus k overall observations in the left. Half of them are in the first 1/3. Half of them are right. So n minus k by 2, n minus k by 2. Right? N minus k by 2 observations off, n minus k by 2 observations. Right? Okay. Now, summation E hat I square upon n minus k by 2 minus 2 is an estimate of the variance of the error term in the first one-third. Is an estimate of the variance of the error term in the first one-third. Right? Similarly, is an estimate of the variance of the error term in the last one-third. Right? Suppose the population variance of the error term in the first one-third is sigma 1 square. Alright? Sigma 1 square. So this is the sample variance upon the population variance multiplied by the degrees of freedom is a chi-square distribution with n minus k by 2 minus 2 degrees of freedom. Right? Okay? So, similarly, this will be what? So if I write it like this, now can this go? I need some more. Similarly, right friends? Okay? So now, if I divide this, what is the numerator, what is the denominator? The numerator is chi-square divided by its own degrees of freedom. The denominator is chi-square divided by its own degrees of freedom. So what is the ratio of 2 chi-squares divided by their own degrees of freedom? Is the F distribution. Right. So what happens is, this goes, because it's being divided by the same. This goes, right, and the resultant is an M distribution minus n minus k by 2 minus 2 degrees of freedom in the numerator and the same number of degrees of freedom in the denominator. Right? Now, under homoscedasticity, if you want to test homoscedasticity with this, what is the hypothesis that you will impose on this? If you have to, sigma 1 square is equal to sigma 2 square. The variance of the error term in the first third and the last third is the same, right? So null hypothesis H naught here, yeah, against the alternative, right? Sigma 1 square is the variance of the error term in the first one third, sigma 2 square is the variance of the error term in the last one third. Under homoscedasticity, we are assuming that all of them are the same, right? So if you impose the null hypothesis, under the null hypothesis, what happens? Under null hypothesis, I can cancel this and this. Because my null hypothesis, sigma 1 square and sigma 2 square are the same. So under the null hypothesis, S1 square upon S2 square will follow the F distribution with n minus k by 2 minus 2 degrees of freedom in the numerator and n minus k by 2 minus 2 degrees of freedom in the denominator. Right? So if you reject the null, you reject the null of no heteroscedasticity. If you fail to reject the null, you say that we cannot reject the null hypothesis of no heteroscedasticity, or which is the same thing, homoscedasticity. So it's a simple F test. Right? So basically it's a simple F test. Right? What do you think will be the limit problems with doing this? So one thing is we can't always necessarily arrange x's in the ascending order, but we suppose think of some way of doing it. Suppose we toss and do something. What other problems do you foresee? Yeah, what are the problems do you foresee? So suppose there were, instead of x, there were x1 and x2, two explanatory variables. Suppose instead of x, there were x1 and x2, two explanatory variables. You will not know which one to arrange, in ascending order. Should you arrange it in the ascending order of x1? Should you arrange it in the ascending order of x2? Actually, you should do both and try. Right? But that will be too time consuming. Right? Okay, if it is only n explanatory variables, you have to arrange everything, do everything n times and so on. Okay. Why do you think we delete the middle 3 of 1/3? What do you think will be the idea of deleting the middle 1/3 of it? We delete the middle 1/3 observation because that gives us the best chance of rejecting the null hypothesis if it is not true. We delete the middle 1/3 observations because that gives us the best chance of rejecting the null hypothesis if it is not true. Why?
The difference is magnified.
The difference is magnified because if the variance of error term, for example, is increasing with x, and suppose continuously increasing, then the difference between the first 1/3 and the last 1/3 will be much starker than the difference between the first half and the second half. Isn't it? So suppose I start with a pitch black color and then I make it a little lighter and a little lighter and a little lighter and a little lighter and eventually it becomes white, right? There is a continuous transition between the shades. If I look at just the first color and the last color, I see the difference much more starkly than if I just saw the first half and the second half. That's the basic idea behind this. Right, so this is called the Goldfeld-Quandt test. Okay, this is called the Goldfeld-Quandt test. Okay, it's a classical test, it's a very famous test, but as you can see, its implementation is a bit of a problem in modern times. Right, so we just teach you this test, but we hardly ever do the Goldfeld-Quandt test. So it's a nice test quickly to interpret and all that. The final problem with the Goldfeld-Quandt test is this works only if the error terms are normally distributed. Only if the error terms are normally distributed does chi-square come into picture and the f come into picture and all that. If the error terms are not normally distributed, then you have a problem with the Goldfeld-Quandt test. Okay, that's one of the major problems. Because you have to specifically make the assumption, no, especially in small samples, that the error term is normally distributed. If it is not normally distributed, then chi-square and all that really don't apply, right? Because the definition of chi-square is x1, x2, xn is normally distributed, so x bar minus mu upon sigma square is standard normal and standard normal square and so on. So x has to be normally distributed in the first place for xi minus x bar upon sigma the whole square to be a standard normal square. And the standard normal square is a chi-square. So error terms have to be normally distributed, otherwise this theorem doesn't work, right? So how do you overcome these difficulties? So I come to the Blois-Pagan-Gottfried test.
which